Hey there, welcome to a video discussing page 3 and 4 of the Unit 1 Lesson 2 notes. Last time we met, we reviewed some stuff on the first page. For example, we talked about mean and median, how to calculate those values, and did some examples. And we actually even put these numbers in Excel or a Google spreadsheet and calculated mean and median. We also discussed quartiles and range. We didn't quite get into standard deviation and variance, so we're going to talk about that in just a little bit. So let's actually go to page 3. First off, let's talk about a box plot. So right before we ended class on Thursday, we wrote down what the minimum Q1, the median, Q3, and maximum were for both North Carolina and New York City. And actually, I could probably pull that up on my end. I just need to locate it. Let's see here. Looks like I closed Google Drive, so that's not smart. So let me pull that up. Okay, I just can't type it. I don't know what's going on. There we go. So this right here should have what we're looking for. Okay, so here are the Q1, Q2, Q3 values for North Carolina, the max, the min, the range and quartile range, and also for New York City. So in the notes, you're being asked to create a box plot for this data. So let's actually do it for North Carolina. So the way a box plot works, you draw a box, you put a line right through the middle, and we call these whiskers. You draw these line segments that extrude from the box, and you draw these little 2 lines as you see there. The min always goes here. The max always goes here. Q1 goes right here. Q2 goes right there. And that's going to be your median, right in the middle. So line the box marks the median, which we call capital M. Lines extend from the box out to the minimum maximum, which I just did. An axis, vertical, horizontal, indicates the scale of measurement, and you label it appropriately. And the central box spans from Q1 to Q3, as I just did. So if we take a look at our data again, here we got Q1, Q2, Q3, max and min, right? And it looks like the min is 5, max is 60. It's all from North Carolina. And of course, 10, 20, 30. So what you probably want to do, if we go back to the notes, is draw maybe a number line, or I guess you could draw a coordinate plane, but we're only going to look at one axis. So say this is at 0, 10, 20, and I'm equally spacing these out. 30, 40, 50, and 60. We'll change colors for a bit of contrast. So remember, our min was 5. So I'll put a little line right there, and our max is 60. A line right there. And then remember, our first quartile was 10. And our third quartile is 30. Our median was 20. So what this kind of shows us is that we tend to see a bit of a skew to the right, because we see the max going all the way out to the right there, where a lot of the data is kind of concentrated in this region over here. So that's how we do for North Carolina. Now for New York City, and actually I'm going to try to stack it appropriately right below the other one. Or actually, let's be smart about this. Let's put them all in the same plot. Let me erase that as well. So, New York City. What was our data there? Looks like it went from 5 to 85, and those were our quartiles, 15, 22.5, and 41.25. So I probably could do now, because I do have the box plot. Let's do a different color. Maybe I'll do green. So still has, and actually we probably should extend the scale as well. So 70, 80, $90, and 100. And we'll do green again. So we have a min of 5, but a max of 85. And then we go out to 15. That's where the central box starts. Go all the way to about 41.25. And the median's at 22.5, somewhere over here. And then we have this right here. So this is New York City. So we see that there's a bit more variation in the data because that center box is a little bigger. And we definitely see more of a skew to the right as well. Because there were some commute times that seem to be really extraordinary, really high. Maybe just a lot of traffic, maybe just some special event going on. You know, it is New York City after all. And we also kind of see that the commute times tend to be a little bit more, a little higher than North Carolina, which North Carolina is, you know, state in the South. Living's a little more relaxed back there. New York City is a little more overwhelming, a little stressful environment. So kind of interesting when you do the data visuals there. But it's good to be able to do this by hand so you kind of get a deeper understanding of how these work. And then we'll start doing these in Excel or R or some other programming language that will make it easier to do these plots. But the plots can be pretty useful here. So let me go ahead and go back to the notes. So that's what we have right there. Now, the central box of a box plot spans Q1 and Q3, as we just talked about, and recalls that this distance is the interquartile range. So remember, Q3 minus Q1 is IQR, the interquartile range. And that means that your data is going to be between the 25th and 75th percentile when you're in the IQR range. Now, we can call an observation a suspected outlier. Outliers are anything that are unusual. You kind of don't expect that data point. Like, for example, I know for me to drive from Sacred Heart to San Francisco, it might take about 35, 40 minutes. If it takes like 3 hours, that would be very unusual, right? Or maybe we could say during rush hour, it takes an hour pre-pandemic. So if you got there in 30 minutes during a weeknight, maybe there's a holiday or something, or we have a pandemic. So it's easy to get to the city now. So usually anything that's 1.5 times the IQR above the third quartile, below the third quartile is called an outlier. So let's look at New York City. So in New York City, Q1 was 15, and Q3 was 41.25. Actually, maybe it's 42.25. Hold on, my memory is not the greatest sometimes. Yeah, 41.25, I got it. Okay, great. So the IQR for New York City is going to be 41.25 minus 15. So I'll use a calculator. I think I could do this in my head, but we'll just use a calculator to be safe. It's 26.25. Great. Now, if I do 1.5 times 26.25, that's usually a rule of thumb we do to identify outliers. We take the IQR multiplied by 1.5, which is 39.375. And what you want to do is add that to the third quartile or to the or subtract that from the first quartile. So obviously, if I do 15 minus 39.375, that's going to be negative, right? In fact, that's negative 24.375. Obviously, I didn't have any commute times that are negative. If I add 39.375 to 41.25, that will be another outlier we could identify. And I believe that's going to be plus 41.25, that would be 80.625. So anything that's 80.625 or higher, or anything that's less than negative 24, which obviously is impossible because we don't have negative commute times, could be considered an outlier. So that's what it says here. If it falls more than 1.5 times IQR above the third quartile or below the first quartile. Well, looking back at our data again, for New York City, we do see one time that was 85, which was our max. And that seemed to be very, very unusual. We can call this an outlier. So definitely we have an outlier. Is 85 an outlier? The answer is yes. Yes, it is. And that's the rule of thumb. How these rules came about, I believe it was a bunch of statisticians that kind of just got together and just figured that's something that they should do. Maybe there's a little more rhyme and reason to it, but that's usually the standard, is you do 1.5 times IQR. And if you're above the third quartile, 1.5 times IQR, then of course we call that an outlier, and of course below. So that's kind of a cool little thing there. Now let's talk about standard deviation. Standard deviation is going to be kind of the key focus for next week. And by the way, we won't do a test next week because I want to spend more time discussing some of these things before we do that. Probably we'll do a test on September 24th. I'll let you guys know on Tuesday for sure. So deviate. Deviate means to go away from. So deviate means to move away from. That's what it means to deviate. And sometimes we want to know, this right here is going to be your observation point minus the mean. So xi is going to be a point that you observe minus the mean. So for example, 85 might have been a point we observed for the New York City commute time, the maximum. And our mean was, we didn't calculate the mean. Why did we not do that? Anyway, real easy, equals average through 1.5. So that would be something I would want to calculate to see how this particular data point, 85, deviates from the mean. And it deviates by about 53.5 minutes, because that's what we're measuring for commute time. So sometimes we want to know what is a typical standard deviation though. So that's what we call the standard. Like do all the data points deviate by this much? No. Actually, if you go back to our data again, a lot of them seem to be pretty close to 30, like 35 or 25 or 30 or 40 or 45. So we want to see what is a typical deviation. Small values indicate small variability. So if you have a small standard deviation, that means that a lot of the numbers are bunched up. And so you don't have as much change. Whereas if you have a lot of a wide range of numbers, like some numbers are really high, some numbers are really low, we call that a large standard deviation. And we're going to do this computation just a little bit. Before you calculate the standard deviation, you have to calculate something called the variance. The variance is a pretty simple calculation, just a little labor intensive. You take every data point, subtract it from the mean, and you square it. So you do this for every single data point. And you divide by n minus 1. N is going to be your total number of data points. We'll actually do it by hand for North Carolina because we don't have as many data points there. And then I'll show you how to do it in Excel or the Google spreadsheet, and then we'll do it in the Google spreadsheet for New York City. You can more compactly express it like this. Remember, sigma means summation, so you're summing all the, we call this the squared mean difference, if that makes any sense. So you're taking a difference with the mean and squaring them. And of course, you're adding all those squared differences and then dividing by n-1. Finally, when you take your variance, which is s squared, if you square root s squared, that gets us what we call the standard deviation. And standard deviation can be very helpful, again, for understanding the variability in your data. You know, did you see a lot of change in your data, or do all the data points seem to be clustered or bunched up? If it's a small standard deviation, they're going to be bunched up. If it's a large standard deviation, they're going to be spread out. So small standard deviation means your data is clustered. A large standard deviation means your data is very spread out. So that's how you can kind of make use of this. Data is very spread out for a large standard deviation. So, looks like that's just repeated. Why are we dividing by n-1? That's kind of an interesting question. So the sum of the deviations, xi minus x bar, always equals 0, so that knowing n-1 of them determines the last one. So yeah, I mean, we do kind of expect that, right? I mean, if you do xi minus x bar without squaring them, if you just do xi minus x bar. So actually, let's kind of do this right here. Let me insert another column here. And let's calculate the average for North Carolina. And so if I did equals A4 minus, I'll do $sign $20. So that way I'm always keeping it the same as for the mean. It's because when I copy and drag, obviously I see that this changes, you know, that's A4 and A5, but I want to keep that the same. So call that kind of like a circular reference. If I were to add up all that, see, it adds up all to 0. So that's what's meant by that in the notes, is that the sum of the deviations always equals 0. So as long as you know every data point except for one, or the sum of the standards, the sum of the deviations except for one of them, you still know them all. Because, for example, if I didn't know this one, then I know that this is going to differ by 37.5333 because I want to get this all to equal 0. So that's why you divide by n-1. Only n-1 standard deviation can vary freely, so we average by dividing by n-1 because the last one depends on everything else. n-1 is referred to as the degrees of freedom of the variance or standard deviation. Some notes about standard deviation, it's always going to be greater than or equal to 0. So 0 means there's no change. It means that if all my numbers were the same, if all my data points were like 1s, let's say, my standard deviation would be 0. So it's never a negative value because you are square rooting. It's measuring the same units as the original observation. So what our standard deviation get for North Carolina times will be in minutes. It's not a resistant measure as calculated using the mean. It is more sensitive to outliers than the mean due to the squaring operation because you are squaring here. So you have an outlier that has a high deviation from the mean. Squaring is going to make it even a bigger number, and it's going to be impacting the standard deviation dramatically. So here, calculate the variance standard deviation for the following data set. So I guess this is height in inches of mature peak booms from new hybrid. I don't know what that means, but anyway, let's just do it. So we're going to fill this out. And then we'll actually do this for North Carolina and for New York City. But we'll do it in the spreadsheet because it's a little easier. So obviously let's find the mean here. So I can use my calculator. The mean is going to be 5 plus 5 plus 5 plus 6 plus 7 plus 8 divided by 6. So my mean is 6. And obviously I have 6 data points. So each observation, 5, 5, 5, 6, 7, 8. And if we do xi minus x bar, I'm doing 5 minus 6, 5 minus 6, 5 minus 6, 6 minus 6, 7 minus 6, and of course 8 minus 6. -1, -1, -1, 0, 1, and 2. If I square all those suckers, then I get 1, 1, 1, 0, 1, and 4. And if I add up all these, I should get 8. Then what I do is I take the summation and divide by n minus 1. So 8 over 6 minus 1, I get 8/5 or 1.6. So that's my standard deviation for my data here. It's 1.6. Then if I square root it, I get 1.26. Now there is going to be a significant thing why we care about this. We're going to do something called a normal distribution. We're not there yet, but standard deviation is going to play a role in helping us understanding how our data should be distributed. So it is going to play a vital role down the road. But for now, you just need to know what it is and be comfortable with computing it. So it's a little bit labor intensive, but that's how we get it. So let's go back to North Carolina again and New York City. So instead of actually, well, actually, let's do this. Let's clear the screen here. So right now I did the difference between these two, but let me actually square these. And then do this. And then I see I have 15 data points. So if I do equals B19 divide by 15, and I want to square root that, so I put a SQRT. That gives me the standard deviation. So that means that a good number of my data points, usually about 2/3 is kind of the rule here, should be about 14.7 minutes off from the mean being 22. So if we have a mean of 22.47, we expect about 68% of our data to follow this range, which would be from anywhere from like 8 to like 36 minutes. That's kind of what, and this is what we call a normal distribution, which we'll have that discussion later in the semester. But for now, just we want to make sure we can compute the standard deviation. So in this case, to do it in the spreadsheet, we're going to do it for standard deviation of a entire population. And I'm just going to highlight that, and you get the same thing. If you do it for a sample, that means that you're doing it for a portion of your data. We're going to talk about that down the road. For now, you're going to pick standard deviation.p. So we see we got the same thing. Now for New York City, I'll do it right here. Standard deviation.p. Just highlight your cells. And you can see that's a little bit more spread out, 21.36. And again, the assumption is that about 68% of your data should be within 21.33 minutes of the mean of 31.5. Let me show you just one other thing that I have found to be quite cool or quite interesting. So as you know, I'm a big football fan. And one thing I've done in some of my analysis of football is to calculate the mean and standard deviation of points scored. I know it seems really simple, but sometimes that gives you a good idea of how well certain teams might be performing. So let me pull up this file. And it's just taking a little while. You just keep waiting. All right, so this was the year 2017. I believe that year Philadelphia beat the Eagles. Sorry, Philadelphia are the Eagles. They beat the Patriots in the Super Bowl. So New England had a pretty good offense, obviously. But anyway, the average points scored for all the offenses for NFL teams in the year 2017 is 21.646. The standard deviation, the population standard deviation was 3.94. So if I were to do 21.647 plus or minus 3.949, I expect 68% of the teams to score within that range. So anywhere between 17.698 to 25.596. So any team that can actually do better than that is probably going to be a pretty good offense, like New England Patriots and New Orleans Saints. And who can't do that will probably be a pretty bad offense. Miami Dolphins are a pretty bad offense. So I expect 68% of my data to fall within this range. Now, what if I take these data points here, and let me actually put that in a different spreadsheet. Actually, I'll just create a new sheet here. Okay, so I have 32 data points. So 68% of 32 NFL teams. So that's 22 teams. So I expect 22 teams to be in that range. Well, let me rank this data. Okay, so obviously these right here don't fit in that range. So I'll highlight those cells. And 25.596, these don't fit in that range either. So if I count it, that's 1, 2, 3, 4, that's 6 teams there and 5 teams there. That's 21 NFL teams, with 2 of those teams that are kind of right on the boundary, or 3 of those teams right on the boundaries. So that's 21 teams, because 11 teams are outside the range, 21 teams are inside. Well, there are 32 NFL teams. 21 divided by 32 is 65.6%. So it's pretty close to that 68%. So what this tells me is that the way that points are scored in NFL tends to follow a normal distribution. Even though NFL teams don't play as many games in other sports, they play 16 games in a full NFL season, the data has some predictability there. And that's something we're going to use down the road to help us to make strong and solid predictive decisions when we have our data. So I love this stuff because it really helps me to figure out how a team's going to perform. Obviously, there are people in Las Vegas that sometimes find this useful, but the stock market is no different than gambling. You're making a speculation on a stock. A lot of financial decision makers have to use this kind of data to make their decisions. Big companies do this all the time. And medicine, they got to look at standard deviation when they're making certain decisions about medical stuff. So you can see the importance of the statistics. Really quickly, before I end the call, as you know, I did make a prediction for the Thursday night football game. And my prediction was actually almost spot on. I had predicted Kansas City to win 34-21, and they beat Houston 34-20. So yeah, if you're impressed, I don't blame you. Just kidding. Should be a little more humble about this. And the only thing that caused us to be off just by a little bit was that Houston decided to go for a 2-point conversion. I mean, it made sense. That's what you want to do if you're down by 24 points, because you get 6 points for a touchdown, 2 points for a 2-point conversion, obviously. So they were like 3 scores away from tying the game, I guess, if they could. But they did make if they went for a kick instead, I would have been spot on with my prediction. How did I make that prediction? Well, this right here is, you could go to a lot of different websites. They give you the point spreads. The total points was supposed to be 54.5, and the Chiefs were favored by 9.5. So what I did was I did 54.5 divided by 2. So if I get a calculator here, 54.5 divided by 2. And then they're favored to win by 9.5. So then if I add that to 9.5 divided by 2, that's actually, hold on. So 9.5 divided by 2 plus 27.25. So they were expected to score 32 points. And if I subtract that from subtracted by 9.5, $22.5. So no one scores 22.5 in football, and 32 is kind of a weird score. So I just did a little rounding, 34 and 21, because 21 is usually 3 touchdowns, 34 is usually 4 touchdowns and 2 field goals. So that's how I came up with my prediction. If you guys are curious, so I didn't do anything too sophisticated actually. I kind of just used the Las Vegas data, and they're usually pretty spot on with their analysis. They try to find kind of the middle road, but that's how I did my prediction. In case you're curious, so I did something similar for the 49ers if the game is played tomorrow, which I highly doubt given the horrendous air quality. So anyway, hopefully you guys learned something here. We will talk more about standard deviation next week. And there'll be a Google form, so please fill that out. And I will see you guys on Tuesday. All right, and be safe out there. It's definitely some crazy air we got.